Hello everyone, welcome back. I'm Mr. Chai. Welcome to another exciting mathematical exploration. Let's get started.
Hi guys, welcome back. Today's topic is vectors, especially lines and planes, including position vectors at the same time. Right now, in order for us to get a better understanding of how vectors work in three-dimensional space, I think it's best we explore a few examples here, so that we can get a better understanding of how this vector works. Right. So now the first question here. We have both lines, L and M, have the vectors given as such. Now, the first one is given here, and then the second one is here. So this is line L, this is line M here. Now, to better understand how vectors work, it's best if we can explore the following question here. The first one, we need to show that whether both of the lines L and M intersecting each other. Secondly, we are going to investigate the angle, the acute angle produced between the two lines there. And then finally, we're going to find the equation of the plane containing both the lines L and M. We have to leave the final answer in the Cartesian form, ax plus by plus cz equal to d here. Now let's get going with this. Now before we start to answer these three questions here, I think it's best if I show you how these both of these lines actually look like in three-dimensional space, right? Now you can see that from here. I have already prepared the lines in three-dimensional space here. So I'm going to give you a few perspective of how those lines look like in three-dimensional space. Right. Now I'm going to now show you here. You can see that this is line L, and then this one is a line M here. Now, from the view itself, it looks as if they are intersecting. All right, now if I rotate it 360 degree from this angle, it also look like they are intersecting. Okay, so this is how it actually look like in three-dimensional space. So I'll try to rotate one turn 360 degree for you to see how the lines actually look like. Yep. So basically, that's how both the lines look like in three-dimensional space. Okay. It's always good to have a visual um, perspective of how those objects actually look like in three-dimensional space before we start to solve any vector problem. Right? Now, since we are clear with what we are looking at, and then we are quite happy with what we are um, able to see. Now it's time for us to explore the algebraic um, perspective, and then which would actually match up with our understanding of the geometrical perspective. Right. Now the first question, to show that both the line L and M intersecting, based on the visual perspective, it looks as if they are intersecting. So this is where they are actually intersecting. All right, now, so, oops, sorry. Just to show you one more time, where the line is. Hold on. Okay. So it looks as if they are intersecting somewhere here. All right. We are going to see where is this in three-dimensional space. All right. Okay. Now, first of all, in order to investigate the intersection point between these two lines here, we will have to solve this simultaneously. Now, before we can do that, let me write down all um, the representations for line L and line M here. Right? So for line L, we have R is given as, I'm going to rewrite in the uh, matrix form, which will be easier for me to interpret. But if you are comfortable with the traditional IJK form, by all means, you can go ahead with that. All right. So in terms of matrix format, it looks something like this for line L. Okay, so that's line L. And then for line M, it will look something like this. Yeah, maybe this one I will just write down L, this is M, easier for us to differentiate between the two. 4, 6, and 1 here. All right. Now the S and T here is basically a parameter um, that is real numbers. All right. Now this is just a scalar um, that is used to represent this particular line. Right. So I hope that is clear at this point. Okay, now it's time for us to show whether they are intersecting or not by equating these two vector equation. So we can actually equate these two together. We are making assumptions that they are intersecting. So if you make assumptions that they are intersecting, therefore both of these vector must be the same at this point here, point of intersection. So maybe we mark this as the x there, for instance. Right? So from here, all we need to do is just rewrite all we have here. All right, there you have it. That's what we have. And then, of course, at the same time, we are going to solve this simultaneously, depending on how you like to solve them in this case. All right. Now, there are many ways to solve this. In general, we will have I'm going to simplify all these equations here. So we will get um, what we have here. We will get S is equal to, it's actually 1 plus S is equal to 4 plus 2t. That's the first row. And then, of course, we can simplify that. Take, for instance, I can rewrite this as 2t, S minus 2t is equal to 3. That will be my first equation. And then I'm going to take the second row here. That will be 1 minus s here is equal to 6 plus 2t. And then thereby, I can simplify this as s plus 2t. All right, s plus 2t equal to negative 5 here. All right, now that will be my second equation. And then it's quite easy to see that we can actually solve equation number 1, number 2 to obtain the value for s and t quite easily. So here, there are many ways to solve this simultaneously. All right, now before that, I'm going to close this window first, show it to you how to solve it um, simultaneously. All right. So from here, we're going to solve 1 and 2 simultaneously. Okay, now there are many ways to do this. Okay, now one way is through elimination. So I'm going to take 1 plus 2 here. So equation 1 plus 2, I will be able to get 2s is equal to negative 2 here. And then hence you can see that, or in this case imply that the value for s must be equal to negative 1. And then from here, we're going to substitute. Okay, we're going to substitute this value back into either one of these. Okay, I'm going to write that down. Substitute s equal to negative 1 into equation number 1, for instance. So if I'm going to substitute this back into equation number 1, then therefore I would be able to get my t equal to, all right, now let me see what do I have there. I will get a negative 2 in this case. So let me see whether that is correct. That is a 4, that's a 3. Okay, that is correct. Right? So that gives me a unique solutions for both the value for s and t here. Right. Now, of course, you should not satisfy at this point having the impressions that uh, they are actually intersecting, right? We still need to verify the last row here. Okay, so for the last row, we have 1 plus 2s is equal to 1 plus a t there. By having the values that we have found out for s and t here, we're going to substitute this into here, right? Or you would like to simplify it before you substitute, also can. So in this case, we can see that both one can be reduced. So here we get t equal to 2s. All right. Now we're going to use these two values that we have found to see whether the third equations tally with our first equation and our second equations here. Now that is pretty obvious, right? If you put in negative 2 there, yes, this is actually true. So the last equation actually give the correct solutions to 1 and 2 also. Therefore, we can conclude that yes, line L and M intersect at one point in this case because there is only one solutions there. The point that I have already marked down just now was x, so we'll use that x there. Like, which point is that? Which point do they actually intersect? If you are interested, all you need to do is just substitute these two values back into either one of these line equations. So take for instance, if I were to substitute my value of s and t back into these equations here, I would be able to find out the position vector of the intersecting point. I label that as OX. That will be very direct. So all I need to do is just substitute this value back into here, -1 here. So therefore, I'll get a 0 for my first row. The second one will be a 2, and then the third one will be a -1. Let me see whether I got it right. Yeah, -1. So this is the point of intersection there. Now, of course, I would always like to verify, even though this is not for exam purpose. This is for analysis point of view. So I would like to find out using the software whether it actually give me 0 to -1 or not. Right. Now I'm going to pause here for a while for you guys to actually check through all this working here. This is how we are going to verify that algebraically for first question, right? Now I hope that is useful. I'm going to show the software one more time. Okay, okay. Now it's a bit messy here. All right, now before that, just let me copy down the answer that we have just now. Okay, so the intersection point is given as OX is here 0, 2, -1 here. The value of s that we have found is -1, whereby the t is -2 here. Right, now those are for reference. Let me erase off this so that it's clearer for us. Okay, now let's get back here. Alright. So this is where they intersect. Let's see whether the intersection point is the point that we have already found out here. Right? Now I'm going to use the help of this software to help us to figure out whether that is true, whether that is true or not. Right? Okay. Now let me see what we have. We're going to find the intersection point. Let me make it larger a bit because this one is a bit okay. Intersection point. Okay, so I'm going to select this both of this line to see where they intersect. Okay, they do intersect at this point here. Let me see whether we got the correct answer here. Now you can see that the point of intersections, which is marked as F here, but previously I marked it as X. Anyway, this is just a label. So it tally with the answer that we have obtained, which is 0 to -1 there. Now, this is the algebraic way of verifying that two lines in three-dimensional space intersect with each other, and then where do they intersect? what is the actual position vector of their intersection point is given here. All right. Now I hope that would clear your understanding of lines intersection. All right. Now I'm going to move on to the second one shortly. Okay. Let's look at the second question now. All right. Now we need to calculate the acute angle between both the line L and M in this case. Right. Now just to show you what we are looking at again, this is line L, this is line M here. Okay, we have already found the intersection point previously. Okay, now we are interested to find out the acute angle between both of the lines there. All right, now I'm going to show you the three-dimensional perspective in this case. You can see that maybe these positions will be much more better. All right, now you can see that from here, the angle that we are interested to calculate is this angle here. That is the acute angle between both the lines there. So we can label that as theta. It is the same as this angle here if you uh, like to use that angle. Right? And then now one way to actually figure out or calculate the angle, the acute angle between both of the lines there is by using its directional vector. All right. Now for line L, here, this component here represent the directions for line L, whereby this component here represent the directions for line M there. Now, this directions vector is very important because it is not bound to any fixed position vector. Of course, based on the usage here, this direction vector is with respect to the origin. So you can see that the pink color arrow and then the blue one. So the pink color vector or arrow here represent the directions of line L, of direction line L here. It is parallel to the line L, and then this is the directional vector for line L, whereby the blue arrow represent the directions for line M here. Now, as you can see that no matter where these vectors are in the three-dimensional space, the angle between these two lines is always given by theta, which is exactly the same as the angle that we are interested to calculate here. All right. Now you can see that this theta is the same as the angle between the two lines. May be acute or obtuse in this case, but here we are more interested in getting the acute angle between the two lines there. Right. So no matter where these vectors are in three-dimensional space, it always gives us the angle between the two lines, whether they are intersecting or not. Right? Okay, so I hope that is clear. In order to find the angle between the two lines or between any two lines, we just have to depend on or rely on the directional vector for the line without taking into account its relative position vector where the line actually passes through, because the line can be passing through any points in this case. The same for both L and M here, right? So I hope that idea is helpful to all of you, right? Because this is the very fundamentals of vector. Okay, now if you're okay with this, let's look at what are the tool or what is the tool in this case that we can use to find the angle between two lines here. So one of the two is called scalar product. Right now, I'm going to redraw this diagram here, so you can see that um, L and M. So this is the directions vector that represent the line L. So I just simply write down line L, and then this is the directions vector that represent line M in this case. Okay. Now I'm going to write down the directions vector for line M here. Okay, so directions vector for line M. So maybe I'll just use a different symbol. I'm going to make a remark here. Directional or directions vector for L is given by here. For L is 1, -1, 2, whereby the direction vector for M is given as this component here, which is 2, 2, 1. Okay, I hope you are clear what this component actually represent in terms of its vector equation. Now that we are going to make use of these two, okay, now just a bit of recap from the side here. The tool that we're going to use is called scalar product. Okay, I'm going to write that down again. Scalar product. Alright, now this is how we actually use scalar product. Now let's assume that this is now in this case this is the directional vector. Okay, maybe I'll redraw that again. Okay, it feels like I enjoy drawing a lot. Okay, now in our case it will be now it will be NM here. This one will be NL. Okay, angle, acute angle between the two lines is given here, and then by using scalar product we will be able to obtain the angle between the two lines using this scalar product formula, that is NM dot product, or sometimes it's called dot product in this case, divided by its magnitude, its individual magnitude. All right, now I hope that is clear. Just a bit of recap here. Now the same goal for this one here. This diagram and this diagram is exactly the same. I just redraw that just for recap. Okay, I hope that is useful. Once we have recapped this, we're going to apply this formula here. I'm going to rewrite here. So that formula says that cos theta, which is given by this dot product. Okay, now how are we going to perform the dot product here? I'm going to demonstrate it shortly here. Divided by the magnitude of each one of these directional vector. Now the magnitude for each one of these directional vector is given by, for instance, for M. Okay, hold on. Here I wrote it down as NL. Order is not important in this case. That will be a 1 square plus 2 square square root. Now that will be the magnitude for directions vector NL. And then we need to multiply that with, okay, maybe I put a big bracket here, with the magnitude of direction vector for M here, which is 2 square plus another 2 square plus a 1 here. Don't forget the square root here. Now this is how it looks like. Right. Right, now in terms of scalar product, all right, now scalar product, I'm going to rewrite here. I'm going to perform the working at the side here. Now, scalar product is quite easy to carry out. Its operation is like this. All we need to do is just sum up the products for each element on the rows there, right? So for instance, the first one is 1 multiplied by 2. That is the product for the first row. The second product for the second row will be -1 multiplied by 2. The third product is 2 times 1. And then once we have obtained all the products, we're going to sum up the products here. So the first one is 2, and then the second one is -2, and then the last one is a 2 there. So the sum of all the products on each rows will give us this. And then that is pretty obvious. We got ourselves a 2 here. And then we're going to simplify this. So there'll be a 2 divided by, okay, so the square root of this, that is actually a 3. And then what do we have here? We have a 6 here. This is square root of 6. Okay, and then there you have it. And then of course, if you like to simplify this and then rationalize this, by all means, right? Now from here, we can use calculator to obtain the angle between the two lines there. Okay, so from here, I'm going to obtain the angle by using its inverse cosine. So we're going to inverse cosine this to obtain its angle there. Right. Now hold on. Just let me clean this up for a while. Therefore, I'm going to obtain the angle by taking its inverse cosine 2, 3, 6 there. And then this would actually give me, all right. Now let me get the calculations going here. Okay. All right. From the calculator, I found that this is 74.2 degree. Now, therefore, this angle 74.2 is less than 90. Therefore, that is the acute angle that describe the angle between the two lines. Now we have managed to calculate the acute angle between the lines here. I'm going to write it down as 74.2 degree here. All right. Now I hope that is clear at this point. Now, of course, I can use the software to verify whether that angle is actually 72. Let me give it a try. If it works, then we use it. If it doesn't, we can discard this. All right. Okay, just let me give it a try. Let me see whether we can do something with this. What else can we have? Okay, let's see. Okay, we're going to do some measurement in this case. So we're going to find out the angle. So the angle between this line and this line here. Now you can see that, okay, that one is not very clear. Just let me show that to you. Now you can see that the angle between the two lines is actually given as 74.221 to be precise. Right. Now we have shown you here how do we apply scalar product to obtain the angle between those two lines there by using its directional vector. All right. Now I hope this is clear for second question. All right. Now I'm going to show you number 3 shortly. All right, let's look at question 3. Find equations of a plane containing both lines L and M, given your answer in Cartesian form. Right. Now, before that, I'm going to show you how does the object actually look like in three-dimensional space. Okay. Now, you can see that from here. This is the plane in green color, for instance. In this case, the color is not very green here. Right. Now, this is a plane that contain both the line L and M here. Now, let me rotate it to show you how the plane actually look like in three-dimensional space. Okay, now you can see that this is how the plane that consists of the two lines that we are working on just now, right? Okay, maybe it's best if I put it to this perspective. It's easier to observe based on our view, right? Now, what we need for this equation is we need to know its vector that is normal to the plane there. So we just need to know one vector that is normal to the plane. All right, now let me show you what do I mean by a vector that is normal to the plane. Normal mean 90 degree here. Okay, so I'm going to get a normal line here. All I need to do is to get this here. Now you can see that. I'm going to rotate that one more round. This line here, this line that I've just created is actually 90 degree. You can see from this perspective, it's actually 90 degree to the plane. The vector that is 90 degree to the plane is called normal, or you can just call it normal line. So we must obtain a normal to the plane, which is given by this line here. So I'll just label this as normal to the plane P, for instance. So we need to work out the normal vector here. Now, one of the two that we can use to obtain the normal vector to the plane is called vector product. Instead of using scalar product, we're going to use vector product, right? Now, vector product. Just let us just recap again. We are still referring to the same vector here. This one is n. Okay, based on this, I will label this as the NL, like the one that we label. And then this one is given by its direction vector M. Okay, here. So this one will be NL. This one will be NM here. Okay. Now, in order to obtain the normal vector, which is in this direction, in this case, so I'm going to show you how it look like. So in this direction, this is the n, the normal vector to the plane. Okay, so one way to do it is by applying the vector product. Okay, now just to recap, vector product. So by using vector product, we can obtain the normal vector to the plane, which is given by vector product, or sometimes it's known as cross product in this case. Right? So I'm going to copy down again, NM. This, just to recap, this part is the direction vector for line L. This part is the directions vector for line M. Yeah. So I'm going to take line M since I wrote it down in this order. Actually, order does not matter at this point, but in terms of vector products, order does make a difference. Just for reference, you have to remember that NM cross product with this is actually the same as the negative NL cross product with this one here. Oops, sorry. That is a cross product with the other one, which is NM here. Right. Now it's in the negative direction. If you're interested to determine the directions of this normal vector, you can apply your right hand grip rules. Yeah, if you're interested, right? You can find out. Okay, from here, I'm going to write this one down as 2, 2, 1, cross product or vector product with this 1, negative 1, 2. All right. Now, to perform the cross product is a bit challenging, but the best way to do this would be we are going to do it this way. From my perspective, I would actually uh, cross this out, not looking at this row. What you are looking at right now are these four elements here. Okay, now all you need to do is obtain this. This section is called the cofactor for the first row. So we're going to work out the determinant for this cofactor. Now determinant for cofactor, I'll just rewrite at the side here. Determinant for reference in this case. So the determinant is given by take for instance, if you have a um, let me see, A, B, C, D. Okay, I did not write down in any particular order here. So if you wish to find the determinant for this, then that will be given by AD minus BC. Okay, now that is how we calculate determinant. So the same thing here. This is the way we calculate determinant. So we're going to cross multiply this and then subtract the other multiplication. So therefore, that actually gives us the first cofactor. So I'm going to write down the first cofactor as, in this case, that will be a 2 or 4 plus 1, which is a 5. So I'm going to write down that as a 5 there. Yeah. And then next, I'm going to continue on with the second one. Okay. All right. For the second cofactor. Okay. For the second cofactor, I'm going to repeat the same procedure here. Now the same thing. For the second one, you're going to cross out this one, and then we will treat these four elements. We're going to use these four elements to work out the determinant here. Right? So based on this, we will be able to obtain. Oh yeah, I forgot my first cofactor that I have already obtained, which is 5. Now I'm going to obtain the second cofactor, which would actually give me a 4 minus 1, which is a 3. But bear in mind, for the second cofactor, we have to apply a negative in front. So that will be a negative 3. And then the same thing, I'm going to repeat that for the last one. So here, I'm going to skip the formality. I'm going to calculate the last one here. You just need to cross out the last part. And then we have what we have here is a negative 2 minus 2, negative 4. So the last one is negative 4. Now, therefore, this would be the normal to the plane, which is given by MP here. And then this would actually show us the normal to this plane, P. All right. I hope that is clear. Okay. Now, next we're going to make use of this normal vector to finalize the equation of the plane. Okay. So I hope that is clear. All right, now I'm going to clean up some of this and then I'm going to work out the equations shortly. Okay, now the last section for this, the equation for the plane. Now we have found out the normal to the plane here. We also know that there is a point OX that is on the plane itself. So we're going to make use of the point on the plane and then the normal to the plane to work out the equation here. All right. Now, by making use of this vector equation for plane, so for any plane equations in three-dimensional vector, we can use this as a formula to represent the plane equation. Now, that would be this case. Oops, sorry about that. I accidentally closed that. Okay, now from here, the equations or the formula for representing the equation for the plane is given by this. All right, now that is what we have here. We have R dot with this, the normal to the plane. And then this A here, I would say that this is a point. It can be any point on the plane itself that you can recognize directly. All right, there you go. This is the equation, vector equations that represent the plane in this case. Okay. Oh yeah, I need to make a remark where the R is X, Y, Z. All right, now I hope that is clear. Okay, now from here, all we need to do is just write down all the informations that we have obtained previously. These are all the informations that we have. Our MP is 5 minus 3 minus 4 here. And then any point on the plane. Now we have already discovered the point intersection between the two lines. It's given by this. And then 5, negative 3, negative 4 here. Okay, now all we need to do is just complete this operation. This is a scalar product. So now that would actually give us a 5 minus 2 times 3, which is, oops, that is actually negative 6. And then finally plus 4 here. Okay, so that would be a 3. I hope that's correct. And then from here on my left hand side, I can write that as 5x minus 3y minus 4z is equal to 3. And then therefore, that is the equations that represent the plane P in Cartesian form. Right. Now, if you are interested to write these equations of plane in vector form, you could have written that in this format. For instance, is equal to a 3. So you can actually leave it in a vector form, or you can write in the Cartesian form. All right. I hope that is useful to you at this point. All right. Now, I will walk through the second question shortly. All right, this is our second question here. All right. Now, with respect to the origin, or points A and B have position vectors given uh, by that vectors there, or A or B. The point P lies on the line AB, and OP is perpendicular to AB there. Now, for illustration, you can see that from this diagram here. Now we have a point A and B, and then there's a line passing through point A and B. Okay, and then there's a point P, which is also lying on the line in this case. Right, and then we also given that our OP, so the line OP or the vector OP is perpendicular to the line that is joining points A and B. All right, now just to show you how it look like over here. So that is the line OP that is 90 degree to the line AB there. All right, now I hope that's clear. Okay, first question. Find a vector equations for the line AB. Find a vector equations for line AB. Now, in order to find the vector equations for line AB, what we need to know is the directions of the vector AB, the directions of vector AB. And then next, we need to know any point where this line passes through. Okay, so the directions for this line AB, I'll write down that as NAB. So we're going to find out the directions that represent this line. So the directions vector for line AB is given by this. Bear in mind, this is just my notation. If you like to use your own one, by all means, go ahead. Right? So the directions vector that represent line AB, which is basically the same or in the same directions as vector AB actually. Now, just to recap again, that is the same as this. Okay, so we have 3, 4, 0, and then A is 1, 2, 2. All right, so from here we have 2, 2, negative 2 there. Okay, now therefore, from here we can write the vector equations for the line. All right, so for line, let's call this, yeah, okay, for line AB, the vector equations that represent line AB is given by R AB here. We must figure out any point that is lying on the line there. Now it's very obvious point A and point B are lying on the line there. Depending on which one you want to use as your anchor, I would say, or as your reference point. So in this case, the typical reference point would be A, for instance. If you like to use B, yeah, go ahead with that. Okay, so we have 1, 2, 2, and then multiplied by a scalar with its direction that represent the line AB here. So we can actually write down the vector equations that represent line AB as such, or you can also write it down like this, for instance. The second way to write this would be here. 3, 4, 0 plus, okay, take for instance, I'm going to use a different parameter here. Okay, there you have it. That's second way to represent the line. You can use the point B here if you like. Okay, or you can also write it down in this form. You can either choose one of these. So take for instance, if I'm using this. Okay. Now instead of using 2, 2, negative 1, because 2, 2, negative 1, they all share a common factor of 2. So you can actually factorize out the 2. Therefore, that is the same as 1, 1, negative 1. Because the factor 2 is also a scalar that is represented by t here. So take for instance, in this case, my t is actually 2 times lambda. Yeah, if you want to represent it in this form. So there are many ways to represent the line equations in vector form. Right? I hope the first question is clear here. Now next we're going to find out what is the position vector for P, which is perpendicular to the line AB here. Right? Okay, position vector P here. Okay. Now, one of the features of this position vector is the vector OP is perpendicular to the line AB there, right? Now, because they are perpendicular, therefore, we can make use of this property. Vector OP is perpendicular to the line AB, therefore, it satisfies these equations here. The scalar product between vector OP and the direction vector for line AB must be equal to a 0 here, right? Because the main reason is because OP dot with this is given by cos theta. Theta is the angle between the line OP and the line AB here. Because they are 90 degree to each other, the theta is equal to 90 degree. Now, if you put in 90 degree into cosine, we will get a 0 there. So that's the reason why it satisfies this equation here, right? Okay. Now, we knew the direction. The directions for AB is given by this one here. So we can actually write down the directions. Now, some of you may like to write the directions as 2, 2, negative 2. That is fine. Or you can use this. Doesn't matter in this case. Okay. Now, the only thing that is missing at this point is the position vector OP in this case, right? Now, we know that the P lie on the lines AB there. So therefore, I'm going to extract this line AB out again. So here I have, instead of writing it in this parametric form, I can also combine this parametric in this way. Yeah, I can write the parametric form in this way. Now, the purpose of writing in this way is to inform us that any points on the line can be represented by these parameters here. Therefore, I can say that, okay, since point P lie on the line AB, I can say that the position vector OP must be given by this. For a specific value of t, of course, right? For a specific value of t, right? And then we get to substitute this one, this equation number one. I'm going to substitute this equation number two back into equations number one there. So therefore we have 1 plus t scalar product with the directions vector. So as I mentioned before, direction vector is there, is equal to a 0 there. So all I need to do is just solve this equation here. So I will have this plus 2 plus t here, and then minus 2 minus t is equal to 0 there. Okay, so from here, let's see what do we have here. We have 2t, we have 3t. Okay, so we have 3t equal to um, this 2t, 3t equal to negative 1. Therefore, the t is equal to negative 1 over 3 there. Alright, now I hope that is clear. Now once we have obtained the t equal to negative 1 over 3, all we need to do now is, in order to obtain the position vector for OP from here, therefore we can conclude that position vector OP, all we need to do is just substitute this value back into here. Now that will be 1 minus 1 third, and then that will be 2 third. Yeah. And then the second one will be 5 over 3. And then the last one will be 7 over 3. Alright, is that correct? Just let me check for a while. Yep. Okay, so that will be the position vector that represent the point P on the line that make a 90 degree between the line OP and the line AB there. Right. Now I hope that is clear at this point. Okay. I'm going to move on to the third one shortly. All right, let's look at third question here. We need to find the equations of the plane which contains AB and which is perpendicular to the plane that consists of the point of origin or AB. Right? And then we need to leave the answer in the Cartesian form. Now before that, I'm going to show you how it actually look like. So I'm going to show you the plane that actually consists of the point of origin or point A and point B there, which is given in the which is given by the blue plane here. So this plane here is the plane that consists of the point of origin and then point A, point B. All right, now let me show it to you. This is the plane, the blue plane is the plane that consists of the point AB. You can see that it consists of point AB, and then also consists of point O there. Now indirectly, this plane also consists of point P, as you can see. Now what we need to find out is a plane that is perpendicular to this blue plane. There's 90 degree to this plane here, which is given by this green plane. So this is the plane that we are supposed to work out its equation in Cartesian form. Right. Now, what do we need for to build a plane equation is the normal to the plane and then a point on the plane itself. Now we do know that a point on the plane for both of these plane is given by the point P there. So we can actually make use of the point P as our reference point to construct the equations for the plane that is perpendicular to the plane that consists of the point OAB. Right? Now the only thing that is missing now is we need to know the normal to the vector of this green plane, the normal to this plane here. Now you can see that from this diagram or from this three-dimensional perspective, it's quite obvious that the normal to the plane that we are interested to obtain here is given by none other than the vector OP. So vector OP is the normal to the plane that we are interested to obtain its equation of. Right? So that's the one information that you need to obtain that from the visual. perspective. All right, now I'm going to turn that one more time so that we can see how it look like. This is the plane, so there's like 90-degree. Yeah, okay, so I'm going to put it like this. Okay, now from here, all we need to do is work out the plane equation. So the plane equation of the plane which contain AB, line AB. Okay, so which contain line AB in this case. All right. So first step is we are going to we knew the point on the plane already, which is given by OP. Now all we need to do is obtain the normal to the plane. So the normal to the plane to this plane uh, P, then maybe we label that as plane pi, for instance. Right? Let's call this plane pi, the green plane. Is actually given by the vector OP. Yeah, it's given by the vector OP, and then that is given by 1/3 of 257 there. All right. Now, instead of writing 1/3 here, because this is a scalar, these sections is actually the directions vector. So either you want to write 1/3 or you can just use this component to represent the directions vector will do also. So in this case, you can write down, or you can write this normal to the plane pi is actually given by 257 there. We can actually drop the scalar in front. Alright. Now the vector equation for plane pi is given by r dot with its normal, and then we must find a point on the plane. Maybe a P or maybe A or B in this case. Now I just want to make a difference here. So since dimension AB is on the line, so we might as well choose either point A or B. All right, now previously I have already made use of point A, so this time maybe I can use point B instead. I'm going to make use of position vector B and then dot with its normal vector. Okay, and then there you have it. All you need to do is, again, I need to make a remark. This one is actually given by Cartesian form this way. Okay, multiply with the normal itself. So the normal itself is here. And then all B is given by 340 and then dot with 257 here. Right. And then from here, we can work out this scalar product. So there's a 6, 9, 15 there. So there's a 15. And then therefore, our plane equations in Cartesian form is given by 5y plus 7z here is equal to 15. Right? Now, I hope that is clear at this point, and then it has been a useful explorations for you. Right? Now, of course, for these questions, without the help of software itself, how would I know that this vector OP is actually 90-degree? Okay, now that is very obvious. You can actually sketch it out. We know that the triangle OAB or OPV itself is basically perpendicular to the plane pi there. So since it is perpendicular to plane pi, therefore you can not only we can use P. Okay, now since P is actually since OP is perpendicular to the line AB, therefore OP must be the normal to the plane pi here. Now I hope there's a bit of logical explorations that you need to perform before we can obtain its vector equation. Right? Now I'm going to move on to question 3 shortly. Right, let's move on to third question now. Alright. Now, with respect to the origin, the position vector of 2 points A and B are given as such. The point P lies on the line A and B, and AP equal to lambda AP. Now, we need to show that OP is given as such. And then number two, by equating expressions for cos AOP and cos BOP in terms of lambda, we need to find the value for lambda for which OP bisects the angle AOB. And then finally, when the lambda has this value that we have discovered, we need to verify that the ratio is actually given as such. All right. Now, before we start with this, let me show you how does it look like, um, or what does it represent visually by this relation here. So the vector AP, okay, vector AP, you can see the vector AP is lambda multiplied by the vector AB there. We have no idea what is a lambda. Lambda could be any real numbers here. Okay, let me show you a simulations of how this look like. Okay, so generally it will look something like this. So the position vector P can be anywhere along the line AP, because it says that the P is actually lying on the line itself. Okay, so it should be something like this, for instance. Okay, give it a while to let you see what we are looking at here. Okay, so the position vector P can be anywhere in the three-dimensional space here. All right. Okay, so that is what it meant by AP equal to lambda AB there. So I hope you get a visual understanding of what does it represent by that, right? So the first question, we're going to show that OP is equal to this. All right, now how are we going to do that? It's quite simple. First of all, we're going to work out the vector AB. So vector AB is given by this. Okay, so from here we have 3, 4, 0, and then OA. So you can see that OA is 1, 2, 2 here. Okay, so from here we have, which is the same one that we have worked out previously. All right, and then AP, whereas the vector AP is given by OP, OA. All right, so that is the same as OP. OA is given by this 1, 2, 2 here. All right, so now we are ready. We're going to use this equation here. It's given that AP is multiple of this. Now, therefore, this is the same as AB. Okay, and then finally we can rearrange this algebraically. So therefore, it's the same as, and then of course we can group them together. Then that will give us 2 lambda. All right, just let me check whether I got the correct solutions here. So 2 plus 2 lambda, and then 2 minus 2 lambda there. All right. So of course you can write in a vector form, or if you prefer to write in a more traditional form, in that case, that will be the same as I, the j component, and finally the k component. All right. So I hope that is clear for the first questions there. Okay. Now I'm going to move on to the next one shortly. All right. Second question. By equating the expression for cos AOP and cos BOP in term of lambda, find the value of lambda for which the OP bisects the angle AOP. So bisecting angle AOB, meaning that it should be this angle should be the same as this angle here. If the line OP bisecting the angle made by AOB in this case. Right? So therefore, the cosine AOP must be the same as the cosine BOP in this case. Right? Now, by using the formula for cosine, okay, just to recap in this case, so I'm going to work out the first one, cosine angle AOP. So cosine angle AOP is the same as OA dot with OP and then by the magnitude itself. Okay, whereby for cosine angle BOP, it will be the same as a OB, OP over OB and OP. Alright, that's how it looked like. And then now all we need to do is just equate these two when the line OP actually bisecting the angle AOB there. Now knowing that OP is given by this one here. Right? So from here, by equating equation 1 with 2, we have OA where OP is the same as OA OP. Right now, notice that in this case, the OP can be removed because they are of the same magnitude in this case. So therefore, all we need to do is just work out the rest here. Okay, so from here, it will be OA with OP. So we have OA and OP in this case. All right. So OA and OP, we will get what do we have here? We have 1, 2, 2. I just rewrite this. With OP, OP is this. Over the magnitude of OA. So the magnitude of OA is quite simple. It's just a 3 in this case. And then OB we have 3, 4, 0. All right. And then over the magnitude for B, which is also very obvious, is a 5 here. All right. So from here, all we need to do is just solve this equation here, and then we should be able to obtain the value for lambda in this case. All right. Now, yeah, I'm going to solve it at the side here. So at the meantime, I'm going to remove this so that we can observe how this can be done. Okay. So from here we have what we have here would be 1 plus 2 lambda So I'm going to write that down. It's a pretty lengthy one to have. So over 3 here is the same as over 5 here, right? And then we could simplify this. Okay, let me see. 9. So there's 9 plus 2 lambda. Just let me check one more time, as I previously made a lot of mistake. Okay, I have made the corrections there. Hopefully you notice the some of the errors there. So 9. Okay, cool. And then next we have here 11 plus 14 lambda over 5 there. Okay, so from here we can cross multiply this. All right. So from here we have 32 lambda, and then that will be, what do we have here? 12. Yeah, it's a 12, right? So therefore, the lambda that we are supposed to get will be 3 over 8. Right. I hope that is clear at this point. All right, I'm going to move on to the next one shortly. All right, the last section, since we have already found out the lambda, which is 3 over 8, all right, now I'm going to write down here the lambda is equal to 3 over 8. Okay, now I'm going to clear all this. I'm going to show you the diagram again so that you can better understand this. So 3, 8. 3, 8 basically means we have AP by AB. So the ratio of this is equal to 3 over 8, which means this length AP is supposed to be 3, and then the length PB is supposed to be 5 here. Okay, now I hope that is clear in this case. And then we also know that the length OA, now we can verify that again. The length OA in this case is given by 1 square plus 2 square plus 2 square here. Square root that. We have already found that previously was 3. And then we can also find out the length for OB. And then in this case, it should be very obvious, it's a 5 there. And then from here, we know that OA over the magnitude of OB is the same as 3 over 5. And then at the same time, we can also write down that the length of AP over the length of PB is also equal to 3 over 5. Therefore, we can conclude that AP, the ratio AP to the ratio PB is the same as the ratio of the length OA to the length OB here. Right, now that concludes the last proof. I hope this is clear. All right, thank you very much for watching. If you like what you're looking at, do click the subscription button and then press the notification bell so that you can get the latest video upload. All right, thank you very much. I'll see you guys again.